Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our 15th part of the video series. In this video, I'll be discussing about the rules required for image formation in convex lens. Then we'll be applying that rule in order to see where will be the image formed when we move the object in front of the convex lens. Okay, and the image that is formed will be looking into the properties of the image. That is whether the image will be real or virtual, magnified or diminished, and how will be the magnification and what will be the modulus of magnification. We'll be looking into that in details. Then after that, we'll be looking into the rules for image formation in concave mirror. After learning the rules, we'll be applying that rule in order to see where will be the image formed when we move the object in front of the concave mirror. And similarly, we'll be looking into the properties of the image that is formed for the concave mirror. And finally, I'll give you a beautiful similarity between the image formed by the concave lens as well as the convex lens. There's a beautiful similarity. I'll share with you that, and yeah, that's all for this video. So without any further delay, let's build the concept. But before that, let's roll the intro. Okay, so let's start with the rules for image formation. So before jumping into the image formation by convex lens, first we need to know the rules for image formation. So we'll be looking into convex lens first. Now, why are these rules important? Because we know in order to produce image, we at least require two rays, isn't it? And the intersection point of these two rays will give us the location of the image. So we require two rays. So these rules will help us to give us two rays. And most of the rules that you see in the screen, you are already familiar with. So let's see. I'll just explain it for you in a single or two sentence and things will be very clear. So let's look into our convex lens rules. The first rule says that if a ray of light is parallel to the principal axis, then after refraction, it will pass through focus. And this is the second focus. This rule we have already learned while learning about focus in our previous video. So this is the first rule. The second rule is that whenever a ray passes through optical center, then the ray will go undeviated. This one has also been described in my previous video. Simple as that. And the third rule is that if a ray of light passing through the focus, that is the first focus, and hit the lens, then after refraction, the ray will become parallel to the principal axis. So these are the three rules that you need to remember. Simple as that. Don't confuse with F2 and F1. Always remember, I have explained it in my earlier video, that is the previous video, that whenever rays are parallel, then it will always, whether it is a convex lens or concave lens, in order to find the second focus, which is the primary focus or the principal focus, we always use parallel rays, isn't it? Now here I have used parallel rays, so the point at which it will meet in the principal axis will be in focus, that is the principal focus. Simple as that. Here we can see after refraction it becomes parallel, therefore this focus is actually the first focus or F1. Okay, simple as that. Don't confuse this thing. Okay, I've seen in students getting confused on F2 and F1, so this is very simple. Okay, now let's move on to our next concept, that is the image formation by convex lens. Let's look into that. Okay, now let's look into the image formation by convex lens. The first one that we'll be learning is that when the object is placed at infinity, and this was the thing that was explained while I was doing it for mirror. Similar concept, I explained it there, that sun is at infinity, so the rays coming from sun actually appears to be parallel, isn't it? So remember one thing, that whenever an object is kept at infinity, then the rays coming from it appears to be parallel. So when object is placed at infinity, what we will do is, we cannot draw the object here. We can see that no object has been drawn here, but the rays coming from it will be parallel. Why? The simple reason is that it is at infinity. Simple as that. Therefore, the rays coming and hitting the lens will be parallel. And we have learned just a few moments ago that whenever rays are parallel to principal axis, then after refraction, what happens? It goes, and for convex lens, it goes and converges at a point known as focus, isn't it? So as you can see, we have taken two rays because we at least require two rays for intersection. So this is the first ray and the second ray, as you can see it here. So after refraction, it converges to a point known as focus. So we will get the image at focus, that is F2. Simple as that. Now let's understand some of the property for the image. So if you look into these points, then you'll see the first point is that the image is formed at F2, and this has been proved from the diagram. Simple as that. Now number two, the object is real and inverted. Okay, I'll explain the inverted part later, but as of now we'll be dealing with real. Now when is an image real? An image is real whenever the intersection of rays are actual. So intersection, I will write it down for you, that is intersection of rays are actual. As you can see that these two rays are actual rays that are coming and intersecting at a point to form the image. Therefore, since these intersections are actual, therefore the image that is formed is actually known as real image. I hope the concept is clear. So what is virtual? We'll look into that a little bit later. That virtual image will be formed whenever the intersection is not actual, but the intersection is actually false intersection. Okay, so in that case the image formed will be virtual. Simple as that. Now inverted, I can't explain here the image is inverted because the object form is very small. As you can see in the third point, that the image produced is highly diminished, okay, as if it is a point image. But as we will be looking into our next location, things will become clear. So don't worry, you'll understand why it is inverted, okay, from the ray diagram. So very simple. The fourth point is magnification. Magnification is negative. Now these things has already been discussed in mirror, so I will explain it very quickly. We know magnification means height of image by height of object. We are just comparing the height of image to the height of object. Simple as that. Now according to sign convention, if this is our coordinate system, if we move up then we take it as positive, if we move down then we take it as negative, isn't it? Now the image formed is actually inverted. Inverted means it is down. The image produced is down. Therefore, we know the measurement always starts from the pole. Therefore, if you want to go down, we need to move in this direction. So the height of the image will be taken as negative. Simple as that. And the height of object will be taken as positive because it is erect, this side, upright. So negative divided by positive will ultimately give us negative. So always remember one thing, that whenever the image formed is inverted, then always magnification is negative. Simple as that. This is very important. I've explained this thing thoroughly while explaining the image formation in mirror. So I'm going a little bit quicker, assuming that you have gone through that video. So magnification is always negative whenever the image produced is inverted, and the modulus of m is always less than 1 because the image formed is diminished. So always remember, when the image formed is diminished or smaller than the object, then the modulus of m will always be smaller than 1, obviously, because as you can see the hi will be small and HO will be big. Therefore, small divided by big will always be less than 1. So we got modulus of m is smaller than 1. Simple as that. So two things you need to remember. Whenever the image produced is inverted, then m will be negative, and whenever the image produced is diminished, then modulus of m will be less than 1. Simple as that. I hope the concept is clear. Now let's move on to our next location. Now the second location is that the object is placed between 2f1 and infinity. That is, it is placed beyond 2f1. Okay, that is, as you can see in the figure, it is placed here. This is infinity, so it is placed between infinity and 2f1. Simple as that. Now how to understand the ray diagram? We know that we at least require two rays for production of image, because only then we can get the intersection point. Therefore, we have taken two rays. Number 1 is this one and number 2 is this one. Since this ray is parallel to the principal axis, after refraction it will pass through focus f2, as you can see, according to the rule. Now the second one is going through optical center, therefore the ray will go undeviated, and we see that the image is produced between f2, that is principal focus, and 2f2. Simple as that. Now let's look into the property of the image. So actually the image is formed between f2 and f1, as you can see in the ray diagram. Simple as that. Now number 2, you can see that the image is real and inverted. Now why the image is real? The simple reason is that the image is formed due to actual intersection of rays. As you can see it here, this line and this ray are actually intersecting. Therefore the image that is produced is known as real image. Simple as that. I hope this is clear. Now the image will be inverted. As you can see it in the ray diagram, that the image is inverted. Always remember one thing, let me write it down for you, that whenever the image is real, it will always be inverted. You need to keep this in mind. Whenever the image is real, the image will be inverted. In the earlier case, when the object was at infinity, we saw that the image was produced at focus, and the image was so small that we cannot explain the thing that it will be inverted. Now since the image here is not that small, we can see from the ray diagram that it is inverted. But in the earlier case, we could easily say that the image was real because the image was produced due to actual intersection of rays. Here also we can see that the image is produced due to actual intersection of rays and the image is real. Since the image is real, it should be inverted, isn't it? In the earlier case also we can say that since since the image was real and it was point object, even though we are unable to understand whether it is inverted or not, but clearly since the image is real, it should be inverted. I hope the concept is now clear. So you need to remember this point. Now the third point is, as you can see from the ray diagram, that the image is diminished. That is, it is smaller than the real object. Number fourth point is magnification. Now when it comes to magnification, m will be negative, and I have explained earlier that m, we know that m is equal to hi, that is height of image by height of object. Since the image produced is inverted, so we will get a negative sign according to our sign convention, and since the object is upright, we'll get a positive sign. So negative divided by positive will get ultimately negative, isn't it? Therefore we got magnification to be negative. So always remember that magnification will be negative only when the image is inverted. So I will just write it here that when the image is inverted, m is negative. And the last thing is that the modulus of m will always be less than 1 when the image produced is diminished. These things you need to remember and keep it in your brain. Okay, so this is all about the image property when the object is placed between 2f1 and infinity, or we can say that the object is placed beyond 2f1. I hope this is clear. Now let's move on to our next location, when we will keep the object at 2f1 and we'll check how the image will be produced and what are the properties of that image that will be produced. Okay, now let's look into that. Now let's look into our next location, that is when the object is kept at 2f1. Okay, very simple. As you can see in the diagram, the ray diagram has been explained here. Now one thing you should understand by now, that what I'm doing actually, if this is our convex lens, then this is our f1 and this is our 2f1 and this is at infinity. What we did in our first case is that we kept the object at infinity, isn't it? After that we kept the object beyond 2f1, not at infinity, but a little bit closer to the lens, isn't it? Now what we are doing is keeping the object at 2f1, that is, we are bringing the object slowly and steadily closer to the lens and checking what's happening to the image. Okay, I hope this much is clear. Now let's look into this. What will happen when I keep the object at 2f1? In order to understand where the image is formed, we need two rays, because we know that in order to get the intersection point we require two rays. So we'll be using two rules, that is, as you can see, this is our first ray and this is our second ray. Okay, the first ray is parallel to the principal axis, so after refraction it will go through focus, as you can see it here. And the second ray is passing through the optical center, therefore after refraction it will go undeviated, and the intersection point is this one, as you can see. And we can see that the image is formed at 2f2. Simple as that. Now let's look into the property of the image that is produced. Number one, the image is formed at 2f2. Simple. Now understand one thing, whenever the object is kept at 2f1, the image will be produced at 2f2. Okay, simple. You need to remember this. Now the image produced is real. Now why it is real? Because the image that is produced is due to actual intersection of rays. Simple as that. And since the image formed is real, therefore we don't have to use our brain. The image will always be inverted. Simple, as you can see it in the ray diagram. And number three, the image produced will be of the same size. Now why it will be of the same size? As you can see that when we keep the object at 2f1, that is double the focal length. We know focal length is the distance from the optical center towards the focus. Simple as that. This is the focal length. So 2f1 is actually double the focal length. Then we see that the image is produced at the same distance, that is 2f, double the focal length, on the opposite side, but the distance is same from the lens. Therefore we can say that the image and the object will have the same size. Simple as that. Therefore the magnification will be our fourth point. We know magnification is height of image by height of object, isn't it? Now height of image is same as height of object. Therefore, we will get the modulus of m to be 1. Simple as that. But m will be negative. Why? Why will be m negative? M will be negative because the image that is produced is actually inverted. Simple. So this is all about the image produced when the object is kept at 2f1. I hope this is clear. Now let's move on to our next location. That is, we'll move the object more closer to the lens. Okay, now our next location is that we are bringing the object more closer to the lens. That is, now we have kept the object in between 2f1 and f1. Earlier we have kept the object here in our earlier scenario. Now it is between 2f1 and f1. So where will be the image formed? So we'll be taking two rays again, very simple. Number 1 and number 2. One is parallel to the principal axis. After refraction it will pass through focus, as you can see. And the second one is passing through our optical center. Therefore it will go undeviated. And the intersection point is this one. And we got the image to be at a point that is beyond 2f2. Simple as that. Now let's analyze the property of the image that is produced. So number 1, the image is formed beyond 2f2, as you can see. Okay, so it is produced beyond 2f2. The second point is the image formed is real and inverted. Why it is real? It is real because the image that is produced is due to actual intersection of the rays. Now it is inverted because it is real. Simple as that. Since the image produced is real, it has to be inverted. Okay, always. Now Our third point is about magnification. Now if you look into the image, then we'll see that the image is bigger than the object, so you can say that the image is magnified, or you can say it is enlarged. Therefore the magnification, that is the modulus of m, will be greater than 1, because we know m is equal to height of image by height of object. Simple as that. Now height of image is greater, that is big, than the height of object, which is small now. Now big by small will be always greater than 1. Simple as that. Therefore modulus of m will be greater than 1. Now m will be negative. The simple reason is that the image that is produced is actually inverted. So simple as that. So m will be always negative because the image produced is inverted. I hope this much is clear. Now let's move on to our next location. And don't worry, I'll give you a story after this and things will be very, very clear. Okay, now let's look at the next location. Okay, now what we can see is that we have brought the object more closer to the lens. As you can see, earlier what was the case? The object was in between 2f1 and f1. Now we can see that the object is at f1, that is more closer to the lens. So what will be the location of the image? Let's look into that. So we'll be taking again two rays, that is number 1 and number 2. So the first ray is parallel to the principal axis. After refraction it will pass through focus, as you can see, and the second one is passing through optical center, so it will go undeviated. Now the funny thing is that these two rays are parallel, and I have written it down here that these rays are parallel, and parallel rays tend to meet at infinity. This thing you need to remember, that parallel ray tends to meet at infinity. That is, it's trying to say that these rays will go and meet at a very, very far away distance, somewhere here, okay, at very far distance at infinity. Now let's look into this property. The property of the image that is produced. Very easy. Number 1, the image will be formed at infinity, as you can see it in the ray diagram. The number 2 will be, the image produced will be real and inverted. Why it will be real? Because the image that is produced is due to actual intersection, which is actually happening at infinity. So you can say that the image produced is due to real intersection, therefore the image produced will be real. And since the image is real, therefore it will be inverted. Simple as that. Number 3. Now third point is magnification. As you can see that the image will be highly magnified. Okay. And our fourth point is the magnification will be negative. Why it will be negative? The simple answer is it will be negative because the image produced is inverted. Simple as that. And modulus of m will be very much greater than 1 because the image produced is very much magnified than the object. Because we know m is equal to height of image divided by height of object. Now height of image is very large. Okay, therefore the division will be very much greater than 1. I hope this is clear. Now let's understand the story, that is the bird's eye view of the 5 locations that we have learned so far, so that you can understand what's actually happening. What is the relationship between the object and the image that is produced? So let's look into that. See, if you look into your notes, then you'll see that we have analyzed the object that is moving from infinity towards the lens, isn't it? The first point that we have analyzed is that the object is kept at infinity, isn't it? And the image that was produced was at f2. Simple as that here. And then what we did is we are slowly bringing the object closer and closer to the lens. Now what is actually happening for the image side? Let's understand. The first point, as we are bringing the object closer to the lens from infinity to f1, see, we have analyzed from infinity to f1, isn't it? These are the locations that we have gone through. Then the image starts moving away from the lens from f2 towards infinity. See, when we kept the object at infinity, we got the image at f2, and when the object was finally kept at f1, this point, then we got the image at infinity, isn't it? So simple as that. When the object is brought nearer and nearer to the lens from infinity to f1, we got the image moving away from f2 towards infinity. So this is the first point of the story. The second point of the story is that as we are bringing the object closer to the lens from infinity to f1, the image starts moving away. This thing you have already learned now, and its size starts increasing. Very important. So let's understand again. So this was our object at infinity, and we got the image that is here as point image, isn't it? Then as we start moving, then what happens? The image also starts moving backward, and the size of the image starts increasing. Okay, now if you look into the third point of the story, it says when the object is at 2f1, then the image is at 2f2. So this is very important. So when we kept the object at 2f1, we got the image to be at 2f2, then the image is of the same size as that of the object. So this is important. So this size and this size becomes equal. So slowly it is increasing, as you can see, and at 2f1 the image size becomes equal to object size. So this is the story till now. So once the object crosses 2f1 and moves closer to the lens, that is, the object is now kept between 2f1 and f1, what we see is that the image moves further away from the lens, and now the size of the image is bigger than the size of the object. So for the first time, the size of the image becomes bigger than the size of the object. So let's analyze that. I've written it down for you, so please take a note of what I have written it down. Now as the object moves more closer to the lens, crossing 2f1, then the image moves beyond 2f2, as you can see in the figure, away from the lens, and for the first time the image is bigger than the object. Very important. Now when the object reaches f1, then the image is at infinity. Simple. So let's look into the figure and things will be clear. Now when we kept the object here, okay, then from the figure we know that the image is produced at infinity and it is highly magnified. So you can see that the size of the image is increasing as it is moving away from the lens and the object is moving towards the lens. So this is the story when we move the object from infinity to f1. I hope this is clear. Now the last point which I need to explain is, this is very important, when we move the object from infinity to f1, okay, all the images that are produced will be real, and if it is real, we know that it will be inverted. Okay, so this is the story or the bird's eye view of the concept that we have learned so far. I hope this is clear. So you need to remember this story. Now we'll be looking into a location, that is when the object is placed between f1 and the optical center. So this is a bit special case, so you need to concentrate here. So let's move on and look into that. Okay, now let's look into this, that when the object is placed between f1 and optical center. So it's very easy. Now let's understand the concept. See, as you can see, the object is kept here, that is between f1 and optical center. So what will be the property of the image, or where will the image formed? So let's look into that. We know for the image to be produced, we at least require two rays. So the two rays that we have taken here is, this is number 1 and this is number 2, as you can see. So this is the ray, number 1 is the ray that is parallel to principal axis. So after refraction, it will pass through focus, as you can see it here. And the second ray that we have taken is passing through the optical center, therefore it will go undeviated. But the interesting fact is that these two rays are diverging rays, therefore they will never meet. We know that diverging rays never meet, isn't it, as I've written it down here? But if we take this ray and extend it behind, as you can see it here and here, then we will get an intersection point that is a false intersection point. This is not real intersection point, a false intersection point. And since that's the intersection point, therefore we will see that the image is produced there. Simple as that. Now since the image is produced there, so let's look into the property that this image will have. So let's study that. The image is formed on the same side of the object. As you can see, yeah, the image is formed on the same side as that of the object. Number 2, we can see that this is virtual. Now why it is virtual? See, all the images that we have got in our earlier cases were real, isn't it? Why it was real? Because the image was produced due to real intersection of the rays. But here, as you can see, that the image that we are getting is due to false intersection, not the actual intersection of rays. Therefore the image is actually virtual. I hope this is clear. And since the image is virtual, we know virtual image is always erect. Now real image is always inverted, isn't it? And we have seen it in our earlier cases. And here we got the image is virtual, and we know virtual image will always be erect. Simple as that. And the third point is that the image that is produced is magnified. As you can see it from the figure, it is bigger than the object, so the image is magnified. This is clear. And the fourth point and the last point is that magnification. Magnification is positive. Why? It is positive because the image that is produced is erect. Therefore, we can see that the HI is, if this is the pole, okay, then our measurement starts always from the pole, so we will be moving in this side. So HI is positive. And again, this is HO, which is again on the same direction, that is upward direction. Therefore HO will also be positive. So we can say M is equal to HI by HO, which is nothing but positive divided by positive, will ultimately give us positive. So we know that magnification is positive when the image is erect or upright. In our earlier cases, we got all the magnification to be negative because magnification is negative when the image produced is inverted. Simple as that. Now the modulus of magnification is greater than 1 because the image that is produced is magnified. I hope this is clear. So this is the property of the image that will be produced when the object is placed between f1 and O. So this is a very special case. I have marked it star. Okay, so you need to remember this is the only case, that is whenever the object is placed between F1 and O, that is optical center, then we will always get a virtual and erect image, and the image that will be produced will be magnified. I hope this is clear. So this is all about the image produced due to convex lens. Now we'll be moving into the rules or the image formation for concave lens. So let's jump into that. Okay, now let's start our study on the rules for image formation in concave lens. So the part for convex lens is done. So let's look into this. The first rule says that whenever a ray of light is parallel to principal axis comes and hits the lens, then it refracts and diverges away. And that diverging ray seems to come from a fixed point. That point is known as focus. This is f2, which is the primary focus of the lens. We know that in order to obtain primary focus, we always use parallel rays, and these are the parallel rays. Therefore, the point that we receive is actually the primary focus, or f2. Simple as that. One thing you need to remember, that for concave lens, the primary focus, that is f2, is on the same side in which the incident ray is. And for convex lens, the primary focus, that is f2, is on the other side in which the incident ray is coming from. So simple as that. You need to remember this. So this is f2, as you can see. So I'll repeat again. Whenever a ray of light parallel to principal axis comes and hits the lens, then the ray diverges, and that diverging ray seems to come from a fixed point. That point is known as the primary focus, or f2, of concave lens. Simple as that. Now the second rule is very simple. Whenever a ray of light passes through optical center, then that ray goes undeviated. Simple as that. The third rule is also very easy. When a ray of light is moving towards f1, then after refraction, what happens? The ray of light becomes parallel to principal axis. Simple as that. So I haven't written down the statement for the rules, but I've given you the diagram. If you just understand the diagram, then you don't need to write down the statement. See, sometimes a diagram speaks more loudly than statement. So that's why I haven't written down the statement. If you understand the diagram, then things are simple. Okay, now let's move on to our next topic, that is image formation by concave lens. Okay, now let's look into the image formation by concave lens. It's much simpler than convex lens. There is only one criteria here, and everything will be almost same. So let's see. Object at any point except at infinity. When we are keeping the object at any point except infinity, and you know why I have written except infinity, I'll explain it later. So first look into this. We have kept the object anywhere. You can pick any point, any position, and keep that object anywhere. Okay, for object kept at any position, we need two rays in order to produce image. So this is our first ray, and this is our second ray, the blue one. Okay, now let's see. Since the first ray is parallel to the principal axis, then after refraction it will diverge. As you can see, this ray has diverged, and the diverging ray seem to come from a fixed point. That point is known as f2, isn't it? So this is f2. Similarly, we know that a ray of light, when passes through the optical center, goes undeviated. So this ray goes undeviated. But the problem with these two rays are that this ray and this ray both are diverging ray, isn't it? Since the rays are diverging, they will never meet. Now, since the rays are diverging, they will never meet. What we will do is we will extend this ray and this ray backward to see where is the intersection point. So as we extend these two backward, we got the intersection point to be this one, and we got the image to be placed at here. That is, the image is produced between f2 and optical center. So the first point here is that the image is formed between f2 and optical center on the same side of the object. So this is simple. So wherever be the position of the object, you'll always get the image between f2 and optical center on the same side of the object. Every time. You don't need to think twice. Okay, one thing you need to remember is it should not be at infinity. Okay, the second point is that it is virtual. Now why it is virtual? Because as you can see, the intersection is not actual intersection of rays, it is false intersection. Therefore the image produced is virtual. I have explained this. And it is erect. We know a virtual image is always erect. So done. And from the figure or the ray diagram, you can see that the image formed is diminished or smaller than the object. So always remember, wherever be the object, doesn't matter, the image produced by concave lens is always smaller than the object. Okay, that is diminished. The fourth point is magnification, and magnification M will be positive. Why? Because the image produced is always erect. Wherever be the object be, doesn't matter. And the modulus of m is always less than 1. Why? Because the image that is produced is diminished. See how easy, simple things. You don't need to memorize anything. If you understand the concept, then things just flow. Simple. Now all these properties will remain same always for the object placed at any position except infinity. Okay, now if you look into this, then both concave and convex lens produce virtual image, isn't it? In our earlier case, like in convex, we have seen that whenever the object was placed between focus, that is f1, and optical center, we used to get virtual image, isn't it? And here we saw that wherever be the object, doesn't matter, the image will always be virtual. So let's see what's the difference between the virtual image produced by convex lens and the virtual image produced by concave lens. So let's look into that. As you can see it here, both concave and convex lens can produce virtual and erect image. But in case of convex lens, the virtual image was magnified. Very, very important. You need to remember this. The virtual image in convex is magnified. Whereas, as you can see it here, for concave lens that we have drawn recently, the virtual image is diminished always. So this is the difference. They can ask you these concepts in objectives, so you need to be very careful. Okay, so this is all about the image formed by concave lens wherever be the object position b, doesn't matter except in infinity. Now we'll be looking into the formation of image when the object is kept at infinity. Okay, let's look into that. Okay, now let's look into this. We are almost at the end of this video. So when the object is at infinity and it is kept in front of the concave lens, then where will be the image formed? Now, if you remember, I told you a story for convex lens, and if you remember the story, then it is similar to that. Okay, let's understand again. So this was our convex lens, isn't it? And if this was f1 and this was 2f1, then we said that if the object was at infinity, then we got the image to be at primary focus f2, and this is suppose 2f2, okay, in the form of point object. And as we started to bring the object nearer and nearer to the lens, then what happens? This image on the other side of this lens starts to move away from the lens, and the image starts to become bigger and bigger and bigger. Okay, this is what I have said. And when the object was placed at f1, then we got the image to be at infinity, isn't it? Simple as that. Now if I flip the story like this, that if the object is at f1, then we will get the image at infinity. Now what we did is we started to move the object away from the lens. Then what will happen? Then the image will start shifting in this direction. That is, it will start moving towards the focus, isn't it? It will start to move towards the focus and the size will go on diminishing, isn't it? Same story is happening here. Let me draw it. So this was the earlier thing that we have seen. Okay, this was the diagram. Now what I did is I brought the object a little bit further away from the lens. Okay, so what will happen? So the parallel rays will remain the same. Okay, so it will meet at this point, because it is parallel to principal axis, and it will meet at focus. So this is same. The only thing that will differ is that the ray passing through the optical center. Now the ray passing through the optical center will be like this, isn't it? Therefore, you can see the intersection point is this. Therefore, the image is moved towards the focus and the size has diminished furthermore. Are you getting the point what I'm trying to say? That whenever I am moving this object towards infinity, then the image moves towards focus. Look into this diagram. I'm taking the object, this object, towards infinity, and this image is moving towards focus and it is becoming smaller. Similarly, when we are taking this object and moving towards infinity, see, there is a beautiful connection. Then this image moved towards the focus and it is becoming smaller and smaller and smaller, and when this object will reach infinity, then this image will become a point object. I hope the concept is clear. Therefore, let's see. Therefore, if the object is at infinity, then the image is formed at f2. Simple. Number 2, virtual. Obviously it will be virtual because as you can see, the intersection is happening here, that is false intersection, not actual intersection. And since the image is virtual, it has to be erect or upright. Number 3rd point is that it will be highly diminished, and as you can see it from the figure, that it will turn into a point image. Okay, and the magnification M will be positive. Why it will be positive? It will be positive because the image formed is erect, and modulus of M will be very smaller than 1 because the image that is formed is point image, very small. I hope this is clear. See how easy it is, simple as that. Now if I draw the ray diagram, then this is the ray diagram. Okay, so we know that whenever object is kept at infinity, then the rays that is coming from that object is always parallel. So this is the parallel rays. So we took two rays that are parallel, and then we can see that after refraction the rays will diverge. But if we extend this and this ray backward, then we will see they will meet at a point called focus, and the image that we will be getting is a point image. Simple as that. I hope the concept is clear and this story is clear. There's a beautiful link between the image formation in concave and convex. It's almost similar. Okay, I hope the concept is clear. So if in your exam this question comes, what will happen if an object is kept in front of a concave lens and then that object starts moving backward? What will happen to the image? You need to say the image will become smaller and smaller and it will move towards the primary focus f2. Simple as that. I hope all the concepts that I've talked about in this video is super clear. So this is all about this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.